Okay, let's unpack this. Imagine peering out into the cosmos, not at some impossibly distant galaxy, but just right next door, our very closest stellar neighbor, and orbiting that star, the potential for another rocky world. It's a place shrouded in mystery, sparking that age-old human question. Could there be another Earth out there? And maybe, do we need one?
It really is a world that captures the imagination, isn't it? Proxima B. It sits there just a stone's throw away in cosmic terms, and yet truly understanding it forces us to confront, well, incredibly complex science. It presents this tantalizing possibility, finding another habitable world, but also throws up these immense challenges that make us question, well, everything we thought we knew about planetary habitability. The core question we're grappling with here is, does Proxima B represent a genuine candidate for a new Earth, or is it something fundamentally, perhaps tragically different?
And that's exactly our mission for this deep dive. We're going to take a close look at Proxima Centauri B, pulling apart what we know about it based on these fascinating sources you've shared, articles from NASAandSpace.com, detailed entries from Wikipedia, and even some insights from a YouTube transcript.
Right. Our goal is to distill all that information, separate the exciting speculation from the hard scientific realities presented in the data you've provided. We want to understand what we truly know about Proxima B, explore the immense hurdles it faces, and see what its existence tells us about the broader search for life in the universe.
So let's start right at the beginning. Its name tells us where it is. Proxima B orbits the star Proxima Centauri, and that star is our sun's very closest neighbor in space.
That's right. When we say closest, we mean about 4.2 light years away, which sounds huge, but in space terms,
It's right there.
it's practically next door. Yeah.
Yeah.
It's part of the larger Alpha Centauri system, although Proxima Centauri itself is gravitationally bound, but quite distant from the main Alpha Centauri A and B stars. The planet is officially Proxima Centauri B, often shortened to just Proxima B.
But we can't just, point a telescope and see it like we see Mars or Jupiter. How did we even find something so relatively close, yet still invisible?
Good question. Its discovery in 2016 wasn't through direct imaging, no. It was a success story for indirect detection methods, specifically Doppler spectroscopy. The Pale Red Dot Project, announced by ESO, that's the European Southern Observatory, used this technique. They look for tiny gravitational tugs, little wobbles, that the planet's orbit exerts on its star, Proxima Centauri.
Ah, the wobble method.
Exactly. As the planet orbits, its gravity causes the star to wobble slightly back and forth from our perspective. This motion changes the star's light spectrum very subtly. Those are shifts in its radial velocity data. By detecting that faint repeating signal, they were able to infer the presence and estimate the mass of the planet.
Okay, so we found it by its gravitational signature, the star's wobble. What does that technique tell us about the planet's physical characteristics, like its mass?
Well, the radial velocity data gives us a minimum mass estimate. The sources provide slightly different numbers as the data has been refined over time. Wikipedia mentions a minimum mass of 1.07 denies unseen 0.06 Earth masses. Space.com says about 1.3 times Earth's mass, and the YouTube transcript gives 1.27 times Earth's mass.
So roughly Earth size, mass-wise?
Roughly, yes.
Yeah.
But the key point here is that these are minimum estimates. We don't know the exact angle or inclination of the planet's orbit relative to our line of sight.
Right.
If we're viewing the orbit perfectly edge-on, we see the full wobble and get the true mass. But if we're looking down more from the top or bottom of the orbit, the wobble we detect is smaller, and the true mass could actually be significantly higher.
Right. It's like looking at a spinning coin edge on versus from above. You see different motion. What about its orbit around Proxima Centauri itself? Is it similar to Earth's orbit? Way out there.
Oh, not at all. Not even close. Its orbit is incredibly tight. It's only about 0.049 AU from its star. Now, to give you perspective, Earth is 1 AU from the sun.
So Proxima B is what? Over 20 times closer?
Exactly. Over 20 times closer to its star than we are to ours. This super close orbit means it just whips around its star incredibly quickly.
Oh, quick.
About 11.2 Earth days for 1 year. Though one source does mention 11.5 days. Tiny difference, but still incredibly fast.
Wow. Okay. And what about its physical size, its radius? Do we know that?
That's another piece of information we don't know precisely yet, and it heavily depends on what the planet is actually made of, its composition. Estimates for its radius range from maybe 0.94 to 1.4 times Earth's radius.
That's a pretty big range, isn't it?
It is. A planet with the same mass but a larger radius would have to be less dense overall, maybe containing more water or other lighter elements compared to a denser, rockier world.
And just to round out the system, the sources mention other potential planets now too, right? It's not alone.
Yes, that's right. Proxima D was confirmed in 2022. It orbits even closer than Proxima B and has a much smaller minimum mass, maybe around 25% of Earth's. There's also Proxima C, which is a disputed candidate, maybe further out. So yeah, Proxima B isn't the only world we think might be around that star.
Speaking of the star, Proxima Centauri itself is nothing like our sun.
Absolutely not. It's a red dwarf star. Specifically, an M-type main sequence star. These are the smallest, coolest, and actually the most common type of star in the galaxy.
Really, most common.
By far. They make up the vast majority of stars, which is why finding planets around them is so interesting. I mean, if planets are common around red dwarfs, there could be a lot of planets out there, potentially trillions in our galaxy alone.
Okay, so how different is it from the sun, scale-wise?
Massively different. It's only about 12.2% of the sun's mass and maybe 15.4% of the sun's radius. Just tiny. And crucially, for any orbiting planet, it's far, far dimmer.
How dim?
It radiates only about 0.005%. That's 0.005% of the visible light our sun does. And an average of about 0.17% of the sun's total energy output.
Wow.
Yeah, this extreme faintness is why, despite being our closest stellar neighbor, you generally can't see it without a telescope, except maybe during its intense flares.
So it's faint overall, but because it's a red dwarf, its radiation spectrum is different, more infrared.
Exactly. And this brings us to the big problems, the big buts. Despite being dim overall, Proxima Centauri is what's known as a flare star.
Flare star, like solar flares, but worse.
Potentially much worse and much more frequent.
Yeah.
Its brightness, its luminosity can increase by a factor of 100 over just a few hours.
100 times brighter.
In flares, yes.
Wow.
It also has a magnetic field considerably stronger than the sun's, roughly 600 plus or minus 150 Gauss, which seems to vary in a 7-year cycle. This intense stellar activity, the flares, the radiation, the magnetic fields, it's a critical, possibly devastating factor for any planet orbiting close by.
Yet Proxima B is so incredibly close that even this dim star still delivers a significant amount of energy to it.
It does. The sources note it receives about 70% of the infrared energy that Earth gets from the sun. And this is precisely why it's considered to be within Proxima Centauri's habitable zone.
Ah, the famous habitable zone, the Goldilocks zone, the region around a star where the temperature could allow for liquid water on a planet's surface, assuming, the right atmospheric pressure. Proxima B is squarely in that zone.
And here's where we hit the absolutely crucial BOUT, which is a major takeaway from the NASA study and the Wikipedia source. A really key point. Being in the habitable zone is really just a starting point. It's a necessary first condition, maybe, but it is not a guarantee of habitability, not even close sometimes.
Okay, explain that.
The definition simply considers temperature based on distance and the star's energy output. It doesn't account for whether water actually exists on the planet or, and this is perhaps most critical for Proxima B, whether a planet at that distance from such an active star could possibly hold on to an atmosphere over geological timescales.
And without a substantial atmosphere, life as we know it would face immense challenges. I mean, it regulates climate, provides surface pressure, shields from radiation, holds the building blocks.
Precisely. It's essential. And this leads us directly into the major challenge for Proxima B's potential habitability.
Yeah.
The atmosphere problem. The sources detail several factors that make it incredibly difficult, perhaps impossible, for Proxima B to hold on to a life-sustaining atmosphere for the billions of years life might need.
First up is that intense radiation you mentioned earlier, the flares and just the general output.
Yes. Proxima Centauri just bathes Proxima B in high-energy radiation. It's estimated to receive anywhere from 10 to 60 times more extreme ultraviolet radiation, EUV, and X-rays than Earth gets from the sun.
10 to 60 times more.
Yeah. And cumulatively, over its long history, it might have received 7 to 16 times more of this harsh XUV radiation overall.
What exactly does that high-energy radiation do to an atmosphere? How does it strip it away?
It's incredibly destructive. This radiation ionizes atmospheric gases. It basically rips away electrons from the atoms and molecules, creating charged particles, ions. As these electrons escape the planet's gravity, they create a charge separation, like an electrical potential, that then pulls the remaining positively charged ions, the actual gas particles along with them, effectively stripping the atmosphere away layer by layer into space.
Wow.
The NASA study you mentioned even modeled this. They put a virtual Earth atmosphere in Proxima B's orbit around Proxima Centauri.
And what happened?
They found it could be lost up to 10,000 times faster than Earth loses its atmosphere.
10,000 times faster. Okay, that's catastrophic.
It really drives home just how hostile the environment is right next to an active red dwarf compared to our relatively calmer solar system. This process doesn't just strip light hydrogen. Over time, it can remove heavier elements too, like oxygen and nitrogen.
So the radiation alone is a huge issue. What about the stellar winds and those coronal mass ejections, CMEs?
An even bigger threat, potentially. The stellar wind, the constant stream of charged particles from the star impacting Proxima B, could be anywhere from 4 to 80 times more intense than the sun's wind at Earth.
80 times.
And the pressure from that wind could be, get this, potentially 10,000 times larger than the sun's stellar wind pressure at Earth.
Okay, that sounds unsurvivable without protection.
Exactly. You need a strong planetary magnetic field to act as a shield, deflecting these particles. And we simply do not know if Proxima B has one.
We don't know.
No idea currently. If it doesn't have a significant magnetic field, that incredibly intense stellar wind can penetrate deep into the atmosphere and physically strip it away, like sandblasting it off over millions of years.
The sources also highlight that Proxima B is likely tidally locked. That's a major factor too, right?
Yes, it's almost certainly tidally locked due to being so close to its star. Just like our moon is locked to Earth, always showing us the same face. This means one side of Proxima B would likely face Proxima Centauri perpetually, experiencing endless day, while the other side would be an eternal night, facing away from the star's heat and light.
And that would create huge temperature differences across the planet.
Extreme differences. Scorching hot on the day side, potentially freezing cold on the night side. This can cause the atmosphere, if it exists, to literally freeze out and collapse onto the super cold night side.
So the air just freezes and falls like snow.
Potentially, yes.
Oh.
While the sources mention that CO2 glaciers on the night side could potentially sublime, turn back into gas, and recycle some atmosphere back to the day side, it's a major challenge for maintaining a stable global climate and allowing for widespread liquid water.
Mm.
And interestingly, there's a twist. If the planet isn't perfectly tidally locked, maybe because its orbit is slightly eccentric, not perfectly circular, then tidal heating from the star's gravity, constantly flexing the planet, could melt internal ice, which might sound good for water. But that same internal heating could also potentially shut down the liquid metal dynamo needed in the core to generate a protective magnetic field.
So you might gain water but lose your shield. That's tricky.
It's a complex interplay of factors.
Mm-hmm.
Then there's the star's history to consider. We talked about flares now, but what about when Proxima Centauri was young?
Was it different?
Oh, yes. Stars go through a more energetic phase when they're young, in their pre-main sequence stage. Proxima Centauri would have been brighter and likely even more active back then. If Proxima B formed in its current close orbit, it might have spent up to 180 million years too close to that brighter, younger star for liquid water to even condense on its surface in the first place.
So it could have been baked dry right from the start.
It could have triggered a runaway greenhouse effect, similar to what we think happened on Venus.
How does that work?
If it was too hot for oceans to form, any water would exist as steam in the atmosphere. Intense UV radiation from the young star would break apart the water molecules, H2O. The lightweight hydrogen atoms would then easily escape into space, while the oxygen might react to the surface or also be lost. Over time, the planet loses all its water.
So even if it started with water, it might have lost it all very early on.
It's a definite possibility.
Mm-hmm.
And the sources mention other unknowns too, like the potential for massive impacts from asteroids or comets. Those could destabilize atmospheres or even boil off existing oceans.
Okay, so summing up the atmosphere problem, it sounds really bad.
It's a formidable challenge. While, yes, processes like volcanic activity could theoretically resupply a lost atmosphere, probably mainly with CO2, and maybe incoming exocomets could deliver some water. But the intense and relentless stellar activity from Proxima Centauri makes keeping any kind of substantial atmosphere, especially one like Earth's, for the billions of years needed for complex life to evolve. Well, it seems like a monumental, maybe insurmountable problem. Different studies even offer conflicting estimates on how much water might have been lost early on. One suggests maybe no more than one Earth ocean's worth was lost,
Okay, that's not too bad.
while another study fears total water loss could have happened within just 10 million years.
Wow, that really highlights just how much we still don't know and the huge range of possibilities, doesn't it?
Absolutely. Immense uncertainty remains.
With all that uncertainty about whether it could even hold on to an atmosphere, what are the possibilities for what its surface might actually be like, assuming it's still there and hasn't been totally stripped?
Right. Well, the space.com and Wikipedia sources explore different theoretical possibilities based on the planet's estimated mass. And that radius range we discussed earlier,
Yeah.
from about 0.94 up to 1.4 times Earth's radius.
So at the smaller end, it could be a dense Mercury-like world.
Yes, if its radius is closer to the lower estimate, one model suggests it could be quite dense, maybe similar to Mercury. It might have a very large metal core, making up perhaps 65% of its total mass. And in that scenario, it would likely have very little water, maybe less than 0.05% by mass, which is actually a similar tiny proportion to Earth's overall water content compared to its total mass,
Yeah.
mostly rock and metal.
Okay, so a dry, dense rock. Or at the other end, the larger radius.
At the larger end of the radius estimate, the other extreme is an ocean planet scenario. This is really fascinating. This model suggests it could be compositionally similar to some of the icy moons we see in our own solar system, the ones that harbor subsurface oceans like Europa or Enceladus.
You mean covered in water?
Potentially.
Uh,
In this scenario, the planet could be composed of perhaps 50% rock and 50% water by mass.
50% water, that's huge.
It is. This could result in a truly massive, globe-spanning deep ocean, potentially up to 200 kilometers or about 124 miles deep.
Wow.
And because of the immense pressure at those depths, that ocean might actually be sitting above a layer of exotic high-pressure ice. Ice formed not by cold, but by extreme pressure squeezing the water molecules together.
50% water. How would we even know the difference from here? A dense, dry rock or a giant water world? That seems like a fundamental difference.
It is, and that's the challenge. Right now, these are just theoretical possibilities based on the limited mass and potential radius data we have. We don't have enough information yet to confirm one scenario over the other. Future observations, like getting a much more precise measurement of its radius, maybe if we get lucky and it does transit its star, or perhaps directly detecting reflected light from its surface, could start to narrow down these possibilities. But it's tough.
And if it did somehow manage to keep an atmosphere and had liquid water, what would the climate be like? The models sound incredibly complex because of that likely tidal locking.
They're incredibly complex. Climate models show a huge diversity of potential states, mainly driven by that tidal locking. You could have a planet entirely frozen over, a snowball state, or a full liquid water ocean world, or maybe mostly dry land. Or you could get these really bizarre scenarios with only localized regions of liquid water, maybe in areas on the border between the hot day side and the cold night side. They're sometimes colorfully described as eyeball planets, with a patch of water looking at the star, or maybe lobster-shaped wet areas.
Eyeball planets, okay.
Subsurface oceans hidden under thick ice are also considered possible, especially if the surface initially froze over, but there's enough internal heat or tidal heating.
And the models have to account for all sorts of complex factors beyond just, how much sunlight it gets.
Absolutely. Because of the potential tidal locking and those extreme temperature differences, you have to model how heat might be transported from the scorching day side to the freezing night side. That could happen through atmospheric circulation if there is one, or ocean currents if there's an ocean. You also have to consider how the intense stellar activity, like cosmic rays, might affect atmospheric chemistry. How water and CO2 might cycle between the surface, atmosphere, and maybe ice caps, the potential formation of thick ice layers or those high-pressure ices, even things like the salinity of any oceans and how currents might behave. It's really complicated stuff.
So circling back to the really big question, the one that drives so much of this research, could there actually be life on Proxima B?
Well, the sources usually define habitability in this context primarily as the possibility of liquid water existing on the surface. And as we've discussed at length, even that is highly uncertain given the atmospheric challenges. And importantly, life that might be confined to a subsurface ocean, hidden beneath miles of ice, like maybe on Europa, that would be extremely difficult, if not completely impossible, for us to detect from Earth with current or even near-future technology. We'd have to go there.
And the setbacks we've talked about for any potential surface life seem pretty significant, almost overwhelming.
They really are. The intense stellar activity, the constant flares, the powerful winds, that's a huge one. The extreme temperature differences if it's tidally locked. And the potential buildup of toxic gases like maybe runaway oxygen or carbon monoxide if atmosphere processes go wrong without biological regulation. It all paints a very challenging picture.
Is there anything positive, any potential upside for life around a star like this?
Well, the main potential advantage that gets highlighted is the star's incredible lifespan. Red dwarf stars like Proxima Centauri burn their fuel incredibly slowly. They can live for trillions of years, far, far longer than stars like our sun, and even longer than the current age of the universe.
Trillions of years.
Yeah. So this offers a potentially vast amount of time for life to emerge and evolve if, and it's a huge if, it can somehow overcome those immediate, brutal environmental challenges posed by the active star, especially early in its life.
So time is on its side if nothing else is. What about things like photosynthesis?
Photosynthesis might be possible, adapting to the redder light spectrum, though perhaps types that don't produce oxygen, an oxygenic photosynthesis, might be favored by the star's light. But even then, any protective ozone layer, crucial for shielding against UV, could be easily destroyed by the star's frequent flares, leaving the surface exposed to dangerous radiation.
Can we actually see if there's life there, or even just get a clear look at the planet itself? You said direct imaging hasn't worked?
That's right. As of now, Proxima B hasn't been directly imaged because it's just too close to the blinding glare of its star. It gets lost in the light. And from our perspective here on Earth, it's quite unlikely to transit, meaning pass directly in front of its star. The alignment has to be just right. The chance is estimated to be only about 1.5%.
So seeing its silhouette against the star is unlikely. But we are actively looking in other ways, right? The sources mention monitoring for signals, like SETI.
Yes, exactly. Projects like Breakthrough Listen are using powerful radio telescopes to monitor the star for potential signals that might indicate extraterrestrial technology. They did detect a candidate signal back in 2019 called BLC-1, Breakthrough Listen Candidate 1. It was interesting because it was a specific narrowband radio signal, the kind SETI looks for.
Was it aliens?
Almost certainly not. Later analysis strongly indicated it was likely of human origin, probably radio frequency interference from Earth-based technology. It's very easy to pick up our own signals.
Ah, okay, so no confirmed signals. What about future telescopes then? Will things like the James Webb Space Telescope or others finally give us a better view?
Well, telescopes like JWST, which is operating now, and the future Nancy Grace Roman Space Telescope, along with the next generation of extremely large ground-based telescopes currently being planned and built. They could potentially observe Proxima B more directly. However, the fundamental challenge remains, separating the incredibly faint light reflected or emitted by the planet from the much, much, much brighter light of the nearby star. It's like trying to spot a firefly next to a searchlight.
So what exactly might these future telescopes look for to learn more about Proxima B, even with that difficulty?
They'll employ sophisticated techniques. They might try to detect the planet's faint reflected starlight, perhaps analyzing its color to hint at surface features, like maybe the glint off an ocean if one exists. Or, more likely, they'll try to analyze the combined light of the star and planet, looking for tiny patterns or dips in specific wavelengths that might be absorbed or emitted by atmospheric gases or hazes. That's how they might look for biosignatures, gases like oxygen or methane that, in combination, might hint at life. They could also look for signs of heat being transported across the planet. If it's tidally locked, detecting heat on the night side would strongly indicate the presence of a substantial atmosphere or ocean carrying warmth from the day side. And there are future space telescope concepts being studied, like HabEx and LUVR, which are being designed specifically with the primary goal of directly imaging Earth-like exoplanets and studying their atmospheres in detail to search for signs of life. But those are still decades away, maybe 2035 or later for HabEx.
Okay, so detection and characterization are incredibly hard, but maybe getting better with future tech. What about the ultimate ambition actually going there, sending a probe?
Right now, with current technology, human spacecraft are simply far too slow. Our fastest probes, like Voyager 1 and 2 or New Horizons, would take tens of thousands of years to reach Proxima Centauri. Voyager 2, for instance, would take about 75,000 years.
75,000 years, yeah, okay. Clearly not feasible within a human lifespan or many, many generations.
Not at all.
But there are these ambitious, almost sci-fi sounding ideas being explored.
Yes. The sources mention concepts like Breakthrough Starshot. This is a privately funded initiative announced back in 2016. The idea here is incredibly ambitious. Launch fleets of tiny, lightweight microprobes, maybe weighing just grams, attached to reflective light sails.
Light sails.
Yeah, sails pushed not by wind, but by powerful, focused laser beams fired from Earth. The goal is to accelerate these nanocraft to relativistic speeds, maybe around 20% the speed of light.
20% of light speed, that's insane.
It is. At that speed, they could potentially reach the Proxima Centauri system in about 20 years instead of millennia. And then signals containing data images, measurements could travel back to Earth at the speed of light, taking another 4.2 years to arrive.
So maybe data in about 25 years from launch, that's actually conceivable. What are the catches? The challenges must be enormous.
Oh, immense. First, how do you actually build and accelerate such tiny probes to that incredible speed using lasers? The engineering is mind-boggling. Then, how do you design sails and probes that can withstand that acceleration and the harsh environment of interstellar space radiation dust impacts? And critically, how do you slow them down when they arrive at Proxima B to actually gather useful data during a flyby? Or do they just zip past? And communication over that distance with such tiny probes,
And collision.
a huge risk. Hitting even a tiny speck of dust at 20% the speed of light could be catastrophic, vaporizing the probe. So navigating interstellar space is a major hurdle. It's very theoretical right now, facing massive engineering challenges, but it is backed by serious scientific research and significant private investment. It shows the level of interest.
So taking it all in, Proxima B is undeniably one of the most fascinating exoplanets we know of. It's right there, our closest detected neighbor beyond our solar system. And it has that really tantalizing characteristic of being a potentially rocky world, roughly Earth-sized, within its star's habitable zone.
Absolutely. But as we've explored, drawing from the sources you provided, its actual potential habitability is anything but guaranteed. It's precarious at best, maybe. The intense radiation, the powerful stellar winds, the frequent violent flares from its active red dwarf star, these are significant, possibly insurmountable obstacles. These forces could easily strip away an Earth-like atmosphere over cosmic time, just like that NASA study modeled with that potential 10,000 times faster loss rate. Unless some unknown, very vigorous process like extreme volcanism or a constant heavy bombardment by water-rich comets could somehow replenish it faster than it's being destroyed.
Right,
We just don't know.
right.
And even its fundamental composition remains a mystery. Is it a dry, dense, metallic core of a long-dead world? Or could it be an expansive, deep ocean planet, maybe with life hidden below? Two totally different possibilities.
What really stands out here, I think, after digging into this, is that simply being in the habitable zone is, well, it's just the starting point. It's not nearly enough on its own. The nature of the star itself, especially its activity level, and the planet's own specific characteristics seem just as important, if not more critical. Things like whether it has a protective magnetic field, exactly how it's affected by tidal forces, its initial composition and water content, all these details matter hugely.
Absolutely. That's a key takeaway. The habitable zone is a useful concept for narrowing the search, but true habitability is far more complex and nuanced. And the effort to find life, or even just to gather more detailed information about a challenging world like Proxima B, is actively driving the development of incredible new technologies. It pushes us. It's inspiring these really ambitious projects like Breakthrough Starshot and guiding the design of future telescopes that promise, eventually, to give us unprecedented views and data about this nearby, yet still profoundly mysterious world.
It really makes you stop and think, doesn't it? This planet, Proxima B, it's right there, cosmically speaking, just 4.2 light years away. A mere step. And yet, it's a world we can barely glimpse, whose basic nature is still largely unknown and whose habitability hangs under this giant question mark because of its parent star. The whole quest to understand it highlights both the absolutely incredible progress we've made in finding planets beyond our own solar system, something unthinkable just a few decades ago, and at the same time, the vast, vast amount we still have to learn about the universe and the complex, probably very specific conditions truly required for life to arise and thrive.
I agree. And perhaps the real significance of Proxima B, right now anyway, isn't solely the chance, however slim it might seem after our discussion, that it might one day be confirmed as another Earth or a haven for life. Its greater value might lie in how it forces us to confront the intricate, multifaceted requirements for habitability, especially under conditions very different from our own solar system. It makes us grapple with the challenges around red dwarf stars, and in doing so, it compels us to innovate, to push the boundaries of our scientific understanding and our technological capabilities just to find the answers. It keeps us looking up, doesn't it? Asking those fundamental questions about our place in the cosmos, and continually expanding the limits of what's possible in our exploration.
A perfect place to leave it for today. Thank you for bringing these fascinating sources and walking us through this deep dive. Stay curious, everyone. Keep exploring these incredible topics, and please join us for the next one.